Okay, so good afternoon. It's a pleasure to now be giving the fourth of my Gresham lectures, and the topic I've chosen is the formation of our galaxy, and this is something that I think we all know very, at least the site of our galaxy, and so if ever you have been to a site where it is truly dark at night, well away from any big city. Unfortunately, London is not the place to be to see this sort of thing. But anywhere, maybe there certainly are remote parts of Europe and Scotland, I imagine, which the sky is very dark. And if ever the weather were clear enough, that's the other condition you need, of course. Then here we are, the Milky Way, most amazing sight. All these are stars, of course, and you can see occasionally patches where you might think there should be stars, but they're not, and these are almost certainly dust clouds in the Milky Way. So anyway, that's what you see in the sky, billions of stars really, which of course you can't actually identify or even recognize unless you use a telescope. So now let's look at what the astronomers plot when they try to make a map of the sky. And so they shift their coordinate system. So instead of the Milky Way, stretching around the sky, it's now equivalent over here, okay? And this would be the north, and this would be the south, okay? There are many, many thousands of stars, and these are all the stars that are in principle visible with the naked eye, a bit fainter actually, with small telescopes. And so this is just counting the stars. And this concentration of stars in this direction here, in this central plane, is our galaxy basically. It's the Milky Way as seen going around the sky at night. Okay, so let's now imagine that we obviously can't, when you look at stars in the sky, you're obviously not penetrating very far in distance. And so there is a way to do this using telescopes, and you look in the infrared, where you can penetrate all the murk and the dust in the stuff that separates the stars, the gas clouds that are everywhere in the Milky Way, and this is what you see. Okay, so here there are probably something like 1 million stars plotted, or photographed, I should say. These images taken with a telescope. And this band now is the Milky Way, and you're looking all the way into the center of our galaxy. Okay, so the center of our galaxy, which is the constellation of Sagittarius, which you can barely see from the north. It's very low down, but in principle, that's the center. Beautifully, this area is much more seen in the southern hemisphere, much more easily. You can see these dark features, which are really rather opaque clouds, but one can see around them and to some extent through them. And all these stars up here are the stars which are in the northern and southern parts of the sky. And over here, you see our nearest neighboring galaxy. This is the Large Magellanic Cloud. A beautiful sight in the southern hemisphere. You can see it with the naked eye, actually. But you can see when you look at this picture of our Milky Way galaxy with these billions and billions of stars, millions on this photograph, but truly there are many, many more that are too faint to be imaged, you just wonder what it would look like if you could look at it from some other perspective, because clearly the sun is the equivalent of being, in this plane. And so we can't get a very clear view of looking down on the galaxy from above. And so what you can do is you can look at nearby galaxies, which are pretty much the twins of the Milky Way. So here is one of them. It's the Andromeda galaxy, basically. And you can just see this as a fuzzy patch in the sky, actually. Very, very fuzzy in the constellation of Pegasus, in fact. With binoculars, you can resolve a little more, and with a moderate-sized telescope, this is the picture that emerges. Again, you see these beautiful spiral structures. What are they? Well, they're the regions which are formed by the spin of the galaxy, where clouds are being crushed together and stars are forming. And all these bright spots are probably clusters of young stars. And in the center, you see this vast concentration of stars, and these are all old stars. You don't see this patchiness, this dark stuff, which are gas clouds, the raw material of stars. You don't see that in the middle. And so this is the core of our galaxy, where millions and millions of old stars are. And here is a satellite of Andromeda, another galaxy, much like the Large Magellanic Cloud is our satellite, but this is a rather bigger one. Okay, so let's have another look at this galaxy. That again is an ultraviolet picture, but let me now show you what it looks like at different wavelengths in the infrared. So here you see it in the optical part of the spectrum, and in the optical you can see not just the very young stars, which are bright in the ultraviolet, but you have a much clearer view of the central part where the older stars are. And this is a scene in the infrared where you're seeing the dust that is being heated by the stars and glowing and showing you where the brightest stars are the younger stars, because they're the stars that burn out quickly, die for a short time, and that's what you're picking out here. And again, you see these wonderful spiral structures with this concentration of older stuff in the center, where there is no evidence for any young stars. So we think this is old, all this stuff is young, recently formed stars. But of course, there are many, many other stars out here too, which are not glowing as brightly as the ones in these wonderful spiral structures. Okay, so let's have yet another view, really face on, of a spiral structure. And so this is one of the most beautiful examples that you can find, taken by the Hubble Space Telescope. And we're looking now at the central parts of a nearby galaxy. So here are the central region full of the older stars. Here are the spiral arms. Why are they dark? Well, these are dust clouds. And in the dust clouds, there are stars being born, and the light breaks through after a little bit as they become more luminous. And it's like, shredding the embryo and the debris in the womb from where they're born, and you can finally see them peeking out. And you see this spiral pattern because the galaxy is spinning, and it's compressing as it goes around. The lanes, the dust piles up in these spiral features, and the clouds do, and that's where the first stars are made. And as time goes on, the stars move around, and then as they age, you see older stars out here. These stars will turn later on. By later on, I mean millions and millions of years. This is just a snapshot. But because we look at so many galaxies at different stages, we can piece together the history of what's going on. So let's imagine now looking at another galaxy that's purely edge on, and I'm going to show you a slightly more extreme one. And again, this is to illustrate the diversity of stuff out there in the universe. So this is almost the opposite of the Milky Way, right? So here we have this region. We call this the disk of the galaxy, what would be the equivalent of our Milky Way, where almost all the stars, young stars are. And now, instead of just a small region full of, maybe 1,000 light years or something full of the older stars, now we have all this spheroidal region of old stars. This diffuse glow, in fact, breaks up into light from many, many stars, packed together so you can't see individual stars. So we call this the disk of the galaxy. It's spinning around. You saw the beautiful spiral structures that wind up. And this we call the spheroid, or the bulge of the galaxy out here. So galaxies are made of these two components, typically. But again, nature is really complicated, and there's more diversity out there. Just to show you one more example, this is a galaxy that is pure spheroid, okay? So this is a giant galaxy. It weighs at least 10 times as much as the Milky Way does, and it's just packed with old stars, so close together that you can't even recognize them individually. So the nearest stars, are light years away from each other and just packed very closely together, fractions of a light year even, in the central regions. Okay, imagine what life would be like on a planet around one of those stars. You would have just this very brilliant, it would never be dark at night probably, in the center of one of these galaxies. So we call these galaxies elliptical galaxies. Elliptical, I suppose, because in 2 dimensions you can track the light shape. It's vaguely elongated, vaguely elliptical. But they're really 3-dimensional spheroids, extended spheroids, ellipsoids, I suppose, is the right name for them. Okay, so that's some galaxies, and again, there are other galaxies that look like this one, and even this one maybe more. Okay, and in this galaxy, for example, you see there's lots and lots of regions. You can vaguely pick out the spiral structure. This is the disk of the galaxy. And in this one, it's just pure disk. There's almost nothing in the center. There's maybe one tiny star cluster in the middle. And so this is the incredible diversity of nature as seen by the astronomers. And so you see some of these galaxies, just look at them. I mean, they look nothing like the ones, if I were to put our Milky Way on here, it would have this, you know, this millions, actually billions of stars in a spheroid in the center. And if I had the galaxy like the sombrero with that huge spheroid, it would, you know, one would see a diffuse glow, a bright glow all the way around. But some galaxies are just pure disks. Okay, so nature is very, very diverse. Okay, but what is the underlying principle behind all this? Well, it's very simple. It's just gravity. It's gravity that holds all those stars together, okay, in place. And so let's go back to think about the founder of our understanding of gravity. And this was at a time when his principal job, Isaac Newton's job, was Master of the Mint. But he was also what in those days one called a natural philosopher. In his case, it meant doing much empirical work, observing nature and understanding nature. And in particular, he was obsessed by the notion of gravity and what caused, you know, the classic story as a child. He was in the orchard and saw an apple fall from a tree or something, and why did the apple go down, etc. Okay, and he realized eventually that the force which explained the apple falling from the tree was exactly the same as the reason why the moon went around the Earth and didn't just go off randomly into space. I mean, it was a force that was scalable. It worked locally on the Earth. It worked, you know, so gravity can work on the scale of, you know, locally, you know, in his backyard, and yet hundreds of millions of miles. Okay, so that's amazing. You know, the Earth to the Sun is 96 million miles, whatever. The Earth to the Moon is well, obviously much less. But anyway, gravity controls why the Earth goes around the Sun, etc. So gravity is there. And so what Newton said was that, and he worried then about why it was that gravity worked to make, you know, the Moon, the Earth, the Sun, the stars, okay? And his idea was that he wrote something like this. In a letter to a clergyman that he was discussing the origins of the universe with, and, you know, Richard Bentley was asked him how he thought the stars were made. And this was Newton's response. If the matter was evenly disposed throughout an infinite space, it could never convene into one mass, but some of it would convene into one mass and some into another, so as to make an infinite number of great masses scattered at great distances from one to another throughout all that infinite space. And thus might the sun and fixed stars be formed, supposing the matter of a lucid nature. Okay, so he hypothesized there the notion of what in modern parlance we call gravitational instability. The fact that the natural disposition of a very large amount of mass, diffuse mass, gas let's say, is naturally to break up into clouds, and those clouds to break up into stars, okay, eventually, okay. That was his idea. But he ran into a slight stumbling block, okay. And he said, well, you know, stars, there are stars and there are planets, you know, and the stars were clearly very bright and shining, but the planets were just, you know, shining by reflected light from the sun. They were relatively non-luminous objects. So this is what worried him. He said, if the sun at rest were an opaque body like the planets, or the planets lucid bodies like the sun, how he alone should be changed, how he could go from one into a shining body whilst all they continue opaque, or they all be changed to opaque ones while others remain unchanged. In other words, by mere natural causes. So he could not understand why his notion of gravitational stability caused planets to form and stars to form, given they were so different. And now Newton was a very religious man, and so at the end of the day, he said he was forced to ascribe this to the counsel and contrivance of a voluntary agent. Okay, we've advanced since then, and now we think we have a much better understanding of how stars form and eventually begin to shine. And the answer is, of course, if I have enough mass, they will collapse and get incredibly hot in the center, and all that heat eventually percolates its way out and gives you light. Okay, and that's the missing ingredient that Newton didn't quite realize, although he got very close. So let's just fast forward and talk a little bit about the modern view of how stars form. And I want to say that this is a very interesting example of the counterbalance between observation that astronomers do and the theories that we have that we try to construct to explain the phenomena of the universe. And so there's always been this delicate balance between the two, because you can imagine if you have a theory of physics, for example, or cosmology, whatever, you want to make sure that theory has some prediction so you can test it. So this is, for example, why astrology is not considered to be a theory, because it makes predictions that are totally wrong. I mean, some might by coincidence be right, but in general, it's a falsifiable theory. And so this is what you aim at doing with your understanding of star formation, okay? And so what we try to do is, starting from first principles, the laws of gravity and so forth, can we actually predict what is the mass of a star? I mean, we know that the sun weighs 1 million times the mass of the Earth, which itself is, many trillions of tons, etc. So can we predict why stars have whatever masses they do, which are enormous? I'll come to that in a moment. And can we understand why it is that some regions make stars, others make stars much more efficiently? You saw that incredible density of stars in the center of the Milky Way. How on earth did that come about, that all those stars packed together? And other regions are quite dark, relatively dark. And can we account for the rate, how rapidly stars form? Because when modern discoveries, we look back in the early universe, we find some galaxies are like our own Milky Way, very quiescent sort of things, making stars, now and then, as our Milky Way does. A few stars on the average are made every year in the Milky Way. But there are other galaxies out there which make stars 1,000 times faster than the Milky Way. Why is that? What on earth is going on? So these are questions that we ask about our theories, and the honest answer is no to all of them. We cannot actually understand this yet. But this is an example, of the progress of physics. I am confident that, maybe in 10 years, maybe in 100 years, we will have the answers. These are very precise questions. We have enormous amounts of data. The answer at the moment is give scientists enough money to build bigger and bigger telescopes. They will answer these questions, okay? And bigger and bigger computers. So this will happen. But I don't think it's going to happen tomorrow. So what do we do in the meantime? Okay, so in the meantime, we need this robust theory. And what we do is we use all the clues that we can obtain with a telescope. So we can look into regions, and now in the infrared we can probe deeply into the regions where stars are forming, and we can see these things, and so we can build together empirical models, right? And then we can try, with all the knowledge that we have of what we see, we can predict how things might happen in some other region, some different galaxy, and one can do a pretty good job. And so in this fashion, in this way, astronomers are making progress and can now do quite reasonable models of star formation, despite the fact that we have no fundamental theory of it. Okay, so here is one of the most important elements of understanding how stars form. So these are two very different regions where there are lots of stars. So this is a young star cluster, okay? And all these bright things are stars, tens or hundreds times the mass of our sun, shining very brightly, short-lived. We know they're short-lived because they ran out of their fuel, their nuclear fuel, really quickly, millions of years. And so we think this whole cluster of stars, formed, tens of millions of years ago. And here, on the other hand, is a very, very old star system. So all the stars here are nothing like these stars. These are rapidly burning stars destined to die in the astronomically speaking, near future, these ones will last as long as, billions and billions of years. Because these are stars like the sun, typically. We can infer what their masses are. And they're intensely clustered. This is what we call a globular star cluster. And this star cluster was formed roughly when the Milky Way was formed. And those stars there are billions and billions of years old. Now, what is amazing about these stars is our sun is approximately 4.5 billion years old. Okay, we know this from dating the oldest rocks on the Earth and so forth, roughly when the solar system formed. These stars are much, much older, okay? They're 4 or 5 billion years older than the sun is. Now, I want you just to imagine, many of these stars will have planets, okay? There's no question of that. My next lecture will be on planets and exoplanets in the universe. And so there are many, many planets. We can't see them directly, but we're sure they're there, okay? And many of these planets will be around stars like the sun. And many of those stars like the sun will be billions of years older than the sun. Okay? Therefore, the planets around them will have had 1 billion years or more advance on the Earth. Now, our history on the Earth is limited, right? Homo sapiens, 100,000 years, whatever. The Industrial Revolution, 200 or 300 years. These are tiny time scales compared to 1 million years, let alone 1 billion years. Okay, so who knows what someday we might find in the as yet undiscovered planets around some of these stars, which are still hard to resolve. So this is a great challenge for the future. Anyway, I'm digressing slightly. I will come back to this in another lecture, but let's now go back to the masses of the stars. And why is it that the massive stars play such an important role, as do the lower mass ones? So here is the number of stars in some region, and this is the mass of the stars. And what this shows you is that here roughly is the sun. This is in units of the sun, so the sun will be over here somewhere. And we see lots of stars that are 1/10 of the sun, 1/3 of the sun in mass. Rather dim stars, but we now see them. And if I ask where is all the mass in this star cluster, most of the mass in this one is in the lower mass stars. The typical stars are half or third. The sun is not special, okay? We're a little more massive than the average. But on the other hand, in this star cluster, we're seeing lots of stars which are 10 or 100 times the mass of the sun. And those stars are very bright, and they control the light. When you look in the universe, you see, especially when you look far away, you're seeing the light from massive stars. And these stars contain most of the mass in a distribution of stars. So when you measure, for example, the speeds of the stars, you're inferring their mass, okay, of the total region about which these stars might be orbiting or passing through. But what is truly interesting for life is the stars in between, okay? The stars that weigh roughly 10 times our sun, those are the stars that explode as supernovae, typically. They have short enough lives that they explode in tens of millions of years. Compared to the age of the universe, that's very rapid. And it's from their debris, which contains iron and carbon and oxygen and silicon, the debris eventually settles down to form some solar system around a star as a new star forms, and from that the planets emerge. So that's what we basically find fascinating about studying the stars at different masses. With our telescopes, we study the light from the massive ones. With our dynamical measurements, we measure the total mass. This controls if the universe will expand forever or not. It's very important, okay? And then in the middle, it's all the chemistry. And so astronomers have to target all of these things, okay? Dynamics for mass, chemistry, you do synthesis by spectra of stars. You can measure elements far away now by technologically by using stellar spectroscopy, and light, you just collect light in the telescope. So all these things play part of a role in reconstructing the universe. Okay, so what is a star? So basically, it's just a gigantic ball of hydrogen gas. Here's the weight of our sun, roughly 10 trillion tons. Its diameter, about 1 million kilometers. So that's what we measure for the sun, 96 million miles away. And why does it stay there? Well, the sun is balanced, okay? It's in equilibrium. Gravity will want it to contract, but as it contracts, it heats up, and it's the heat from the center that gives it a precarious equilibrium. And that heat is maintained by thermonuclear reactions, the same things that we're hoping to tame on the Earth one day to make fusion reactors. We already use when we occasionally explode hydrogen bombs. The same physics controls the center of the sun and gives it the supply of heat until you run out of fuel, hydrogen fuel, and then the star will collapse. So our sun is good for another 4 billion years or so. We don't need to worry too much, and in 4 billion years, who knows what might happen to the Earth. So right now we have we're worried about, will we stay in Europe or not over the next, 6 months or whatever. So these are different time scales, right? No politician is going to worry about the billion-year time scale, unfortunately, I think, but still. Okay, so here you can see a star being born, okay? So, again, pictures taken from space with the Hubble telescope. You can see these dark clouds, and in this cloud over here, a massive star is shredding the dark womb that surrounds it, emerging. And this now is the common sign of a star that probably is much more massive than the sun to give all this light, but surrounding it there are most certainly are lower mass stars as well, sun-like stars. Many will be born at the same time as companions of this star. And so that is how the star looks. So what is the recipe to make a star when we try to understand what's going on here? So it's really fairly straightforward. You start off with this big cloud of diffused hydrogen. It turns out there's an admixture of helium as well. Helium was actually made in the Big Bang. It's one way we connect stars and cosmology. It's quite amazing. And it was actually first discovered in the sun before it was even found on the Earth by spectroscopy in the sun, and then found to be fairly common on the Earth. And of course it has its uses on the Earth, but it's basically not critical for forming stars. It just is a third of the mass, that's all. And the interesting stuff is the 2% of this cloud, which is the carbon, the oxygen, the iron, the reason that we're here, basically. And this heavy stuff came from previous generations of exploding stars that, enriched themselves in the center by thermonuclear reactions. The debris dispersed, eventually came to form a new star, a new cloud, and that is why the sun is here. Okay, and so gravity then brings this cloud together, and the cloud spins up as it compresses. It's got some small spin, it spins up faster and gets thoroughly mixed. And eventually, gravity is so important that the cloud begins to break up. Okay, so why does this cloud, which is not maybe much, this may be hundreds of times the mass of the sun, whatever. The typical clouds we see are millions of times the mass of the sun in the Milky Way. So what on earth happens to this cloud? Well, it fragments into smaller and smaller things. That's what happens. And the process of fragmentation, which is the key to star formation, was invented by James Jeans about a century ago. And his idea was that as any cloud compresses under gravity, it gets hotter. So you have a balance between the two forces. But the cloud can lose energy just by radiating to space. So pressure loses the battle. So smaller and smaller bits of the cloud have gravity dominant, and this is the process that Jeans called fragmentation. Okay? And so the idea is you start off with some typical mass for the cloud, and it gets smaller and smaller, and down to a typical fragments or a fraction of the mass of the final star that's going to form, maybe even 1% or something, really, of the mass of the sun. And then, finally, these fragments become so dense and so opaque, they stop radiating. The radiation can't escape, and then they start sticking together and building up. And so you end up, first, it's a bit like Humpty Dumpty. First you break it up, and then you build it up again, and somehow then you end up with the mass of a star when it starts shining, and the pressure becomes high enough, the heat becomes high enough to drive off the debris, and you end up with a star. So it may seem totally crazy to you. Why do we come up with a star? Well, the answer came from Englishman number 3 in this story, Sir Arthur Eddington. And so he had this really brilliant idea. He said, imagine you're living on a planet always covered with clouds. He said you could conclude there had to be stars. What happens is the stars. And so it's an amazing idea, and it was based on an advance on, the Newton-Jeans idea of gravitational instability. It was one step beyond, a very important step beyond. And so he said that if you imagine you have too big a globe of gas, then it will blow itself up because it'll be so hot the radiation will just blow it apart. Okay? That sets an upper limit. And he could calculate that this upper limit was roughly 100 times the mass, 50 times the mass of the sun. That's what he said in 1926. Okay? He also realized that if this globe of gas was too small, it would be too cold in the center, the pressure would be less, and so it wouldn't glow. So he said there had to be a range between his calculations. That was all he did. This is just pure back-of-the-envelope type theory between 1/2 and 50 times the mass of the sun. It's a truly amazing prediction of physics, I think, okay? And he had no idea at the time of the source of the energy that keeps stars going for a very long time. That came later when the whole idea of nuclear reactions was applied to stars. But it didn't matter for his argument. These things had to be there, okay? Okay, what then comes out of all of this? Well, there is... here's what our sun looks like. And so you can see it's not the usual view of the sun. This is taken with an X-ray telescope. But you can tell that in the center there's vast sources of energy, and they heat up the outer part of the sun and give you this amazing coronal display that you can even see in a full eclipse, some glimpse of this. But this is taken with an X-ray UV telescope. And it reminds me of the following quote that applied to something else from Stephen Hawking. What is it that breathes fire into the equations and makes the universe for them to describe? And this is literally, breathing fire into the equations. And, this is what came out of Eddington's and equations, basically. There had to be this source of energy which, caused all this heat to emerge. So that then is the sun. What about its neighbors, okay? So here again are close-ups of different examples. And so stars in some regions, not our sun, but they're closely packed. So our nearest neighbor is Alpha Centauri, which is roughly 3 or 4 light years away. This region is, a few light years, 10 light years, 10 or 20 light years across, and it's packed with stars, okay? So imagine life on a planet around one of these stars. The sky would be totally different. This is an older star cluster, and this is a younger star cluster again, where the star formation is ongoing, and you see all this. This would be a more dangerous place to live because a lot of these massive stars are much more bright in X-rays than the sun was. The sun's has a very dim corona, relatively speaking. It's glowing a bit in X-rays, but some of these stars are tremendously bright and would probably irradiate, any planets that were within that region, and life might be tough in there. Okay, so then now it's the turn of the astronomers to try to understand how it is that stars are made. And so the tool that is used is that of taking a large computer, putting down all the equations that describe gravity and pressure and how these forces counteract and first break up, okay? Basically, it's fragmentation that's being studied. That's the primary process. And they try to understand how a cluster forms by a numerical simulation. And even though you don't understand the details, exactly why a star has got a certain mass, as I said at the beginning, one makes reasonable assumptions, and one tries to see whether you could start off from those assumptions, which make one star, whether you can make a whole cluster of stars. So let me show you an example of a numerical simulation carried out at the University of St Andrews by Ian Burnell. Okay, so this is the birth of a star cluster. So he's looking at the gas basically fragmenting around little clumps, and the clumps grow bigger and bigger. All this diffuse stuff is the gas reservoir from which everything began. You can see more and more particles growing, and so this looks not unlike one of these star clusters. There was a very massive star in here that cleared out a whole region around it. So there are rather few stars, but in other regions there are big clumps of stars. So that roughly is how a star cluster is formed. Now, astronomers don't stop here. I want now to tell you about the context in which all of this forms. Okay, so now let me just jump back into the early universe. Okay, so structure is developing. I'll come back to the details of that structure in a moment. But again, numerical simulation gives us the clue. So let me just jump straight forward into that. So here is a simulation from when the universe was young up till today, and you're watching structure form. So these are not stars. These are entire galaxies, okay? This is going to be the Milky Way. So this is many, many small galaxies merged together to make this one big one. And so this is our modern understanding of how it is that structure forms. I'll try to explain where this picture comes from in a moment, but it's based basically on looking back into the early universe and trying to understand. And so here is a cartoon of how the structure forms. So early in the universe, you have many small clumps, and they sort of merge together and make one very big galaxy. Now, what I have to tell you is there's one secret in this I didn't mention, is that when we looked at the stars, it was ordinary stuff, the stuff that the sun is made of, hydrogen, helium, carbon, iron, etc. In cosmology, we know that most of the universe is dark. We call it dark matter, very weakly interacting, but it controls the gravity of the universe, basically. So first those dark regions form, and then in them, the ordinary stuff, the baryons, the stuff that stars are made of, condenses, and the visible parts of galaxies form. So this is meant to be, this is an illusion that this is visible. This is all dark matter, okay, as this is too, okay? And so really, it's the dark clouds that form the context for the disk of the Milky Way to form and all the other stars to form. Okay, so let's now go back one step beyond this, okay, into the deep past of the Big Bang. So this was the picture from when the universe was 1/10 of its present size, our best understanding of how structure developed from something more or less homogeneous. But you notice one began with fluctuations, nevertheless. Okay, things were not totally uniform, otherwise there would be nothing to form at the end of the day. So where did these initial seeds come from which the structure was made? Okay, so here we get into the very frontier of physics today, and this is something we really have no full understanding of, to put it mildly, okay? So the reason is that we're convinced that these fluctuations from which structure made, they can only come from the quantum theory. The quantum theory applied to gravity, and we have no such theory. We can speculate about this theory, but Einstein spent all of his life after he developed his theory of gravitation trying to unify with the quantum theory. Gravity is a theory of precision, of certainty. The quantum theory ultimately is a theory of uncertainty. It applies on the microscopic scales. Obviously, we know how many people are in this room. We're not losing people. Things are quantum stable in some sense in this room, but on the very tiny scales, things come and go on time scales so short that you can't actually measure them, and that's the essence of quantum theory. But at the beginning of the universe, we must have some way of unifying these things together because things are so dense, so extreme that the quantum theory must apply, but so does gravity as well. And we have no theory of what this is. Okay, maybe some of you have been hearing the Reith lectures, but Hawking, I'm sure, would have, telling you a lot about these mysteries. Okay, anyway, we're sure that this quantum stuff is there. First of all, we've discovered it in terms of what we call dark energy, which gives an acceleration of the whole universe. That's another lecture. But what this does leave behind are tiny fluctuations, wrinkles in space and time, if you like, that are so short-lived that they just come and they go, as quantum theory says things should on the tiniest scales. That you can never actually measure something because the act of measurement already gives you someone perturbs whatever it is you're measuring. Okay, so you don't know exactly what is there. And that's the essence of what we call the uncertainty principle of Heisenberg. And so this means it's something really curious. It means the weirdest things can exist in the universe if they last a sufficiently short time. Another way to put this is that the weirdest things can happen to you if you wait long enough. I mean, in principle, there'd be quantum fluctuations in the floor of this room, and you would fall through the floor. But this would, of course, take many, many, many billions of years, so it's very unlikely today. But nevertheless, the quantum theory says this could happen. Likewise, it says at the beginning of the universe, very strange things could happen too. And so one implication of quantum theory is that there was a particle discovered a couple of years ago, the missing link in our standard model of physics called the Higgs boson, found in the Large Hadron Collider, and these particles, which they found a handful by having this amazing experiment, which collided things at extreme energy together in this tunnel that's 50 kilometers in circumference around Geneva, and so you have these beams of protons, things are going in opposite directions, they collide together, and there's a debris that comes out, and finally you find this elusive particle that everyone was looking for, conjecturing had to be there. They finally found it. Okay, so what this quantum theory, origin of the universe idea, tells us is these particles are not just lasting for picoseconds in this collider, but they're everywhere. They're just coming and going all the time. Okay, we just can't see them. But what we do see is the manifestation of all this rushing around gives you a certain amount of energy, okay? And we call this, some call it the dark energy, some call it the energy of the vacuum, the energy of nothing, but it's this energy that accelerates the universe. That's responsible for these initial seeds that control the universe. And the reason that we're so sure that this is the explanation is that when we look at this wonderful picture taken with a Planck satellite of the microwave background. So this is the radiation from the beginning of the universe, okay, that last comes to us fills up the whole sky. It's one of the most important bits of evidence for the Big Bang. When you look at this radiation, you see these slight variations from place to place. And the problem is these variations occur, all over the place, and they can only be explained by quantum fluctuations at the beginning of the universe. Nothing created them in any terms of physics that we understand. So this is physicist's explanation for the origin of these fluctuations. Now you may say, fine, this is a great conjecture, but it has led to an amazingly interesting theory of how we put together the universe we see. And so here is that theory. Let me just try to summarize it for you. So the idea is you begin with just tiny fluctuations. That's what this line signifies. Just fluctuations and this is the scale. Small scales, tiny scales, fractions of the size of an atom to the most enormous scales you can imagine today. The quantum theory, if we had one, should predict there are fluctuations everywhere, and that's a conjecture. But if there are these fluctuations, we just take that. If that's how the universe began, we don't have this precise theory yet, then as time goes on, they lead to density fluctuations, that's the green line, and the smaller ones have more time to grow, so they're bigger, and this is what gives us the seeds, the wrinkles in space-time for which all structure grows. So that's the conjecture from theory. Now this is a theory which may seem so far-fetched to you that, you could say it's just mythology, except for the fact that the difference in mythology is this theory does make certain predictions, okay? And so we go out, we look for these predictions, okay, to try to see if this idea is right or not. And here are examples of these predictions, okay? So when you take this theory, this green line translation of this line over here, these are looking for larger and larger things in the universe, and this is the prediction of the inflation theory that things should line up, okay, on this line. Small things should form earlier, this is their density actually, or when they form. Small things form first, and then bigger and bigger things build up. And when we look around the universe, we see all these amazing things that just fit into place, okay, from this theory of the quantum fluctuations. And maybe the most amazing thing of all is when we look at this background radiation on the sky, that fits exactly the prediction of this very, very simple theory. Okay, so let me now go back to dark matter, which is this dominant. So this is the Milky Way, right? Again, here we are. But we're surrounded by this vast, and we know it's out there, I'll explain why in a moment, because of a prediction that was made by Kepler, basically. So what Kepler noticed is when you looked at the sun, the planets moved with slower and slower speeds as they orbited the sun. And the reason was that Kepler realized that the gravity of the sun got weaker the further away you go. So their orbital speeds had to be smaller. And so you predict then that if indeed there's all this dark matter out here, this was not predicted, this is a big surprise actually, but if there were all this dark matter out here, and the speeds of stars, if you saw it here, would not go down because there was extra gravity, unlike the case of the sun. And so this indeed was observed. It was a complete surprise. The astronomer who did this first was Fritz Zwicky. He was an amazing iconoclast for a physicist, astrophysicist. He had many brilliant ideas. He was the person who first had the idea of there should be tiny compact stars called neutron stars, now pulsars, and exploding stars. But maybe he's best known for his idea of dark matter. And you can see him, he lived for many years. He was a Swiss origin, but then worked in California for many years. And he was very critical of his colleagues. And so this was a gesture that he loved to make, indicating that this person, who may have been a rival of his, who knows, is a spherical bastard, okay? Let's say, whichever direction you look at him, it doesn't matter, okay? Anyway, so then Zwicky, as a slightly younger man, making his discovery. So this was in 1933. And so he realized that if I look at this system of galaxies, this is a modern photo, but it's the same system he studied, called the Coma Cluster, he said that there must be das dunkle Materien, dark matter. Okay, otherwise the galaxies would all fly apart. And the reason his prediction, which was 50 years ahead of its time, really, is known to be right, is that with modern observations, when we do deep images of this cluster, we find background galaxies have these weird shapes, okay? Actually, this is slightly exaggerated. These are extreme cases, but all these fainter ones, which are seen behind the cluster, and if you plot the pattern of distortion of the galaxies, then you come up with a map. This is a distortion map. And this is a map of dark matter, telling you this entire cluster of galaxies is basically a cloud of dark matter, which is the reason why the galaxies are not going off into nowhere. They're staying in this cluster around them. And these are galaxies like the Milky Way. Now, the same is true for stars in the Milky Way. And this was the work of two other astronomers in the 1940s and 1950s, mostly the 1950s. And so Vera Rubin, who was one of the first eminent female astronomers who worked at Mount Wilson, and that was at a time when it was very rare to have females, and so all the facilities at the top of the mountain, you would observe at night, of course, there were none for women. And so she had to, go down at the end of every night to catch some sleep or use the bathroom or whatever, and then return to process her data. In those days, they used photographic plates. The astronomer would develop his own plates, etc. And so it was tough. But anyway, she succeeded in looking at our neighboring galaxy, the Andromeda Galaxy, measuring speeds of stars and finding they didn't go down where you ran out of light, just like Kepler's laws would say they should, but kept on staying roughly constant. And then a radio astronomer made her result even more powerful, because he showed that you could even see gas clouds out here where there were no stars, which also were orbiting the Milky Way, under the force of this unseen gravity, this unseen matter. So this is sort of the way it goes. As you look from the center of the galaxy, this is what you expect to see. The speeds of orbit of objects should get smaller and smaller, as Kepler told us they should, as you move further away from the light. But instead, you see them roughly approaching a constant, telling us that the only thing that can do this is dark matter. And this is not just true for the Andromeda. It's true for everything. And so this is a recent compilation of data showing you for many, many galaxies, as you go farther away from where the light is, things just hang on in there. Dark matter everywhere. So here we are. This is the universe as it stands today, full of dark energy, which I'm not going to say much more about, but an awful lot of dark matter, and the stuff that we're made of is a mere 4%. And what we can say is that we don't know what the dark matter is yet, but there's certainly a lot of it. Okay, so let me show you one or two examples which have come from the numerics. So before we did big computer simulations, your naive model of what a dark halo was this, okay, a big amorphous blob of dark stuff. Here is one of the few discoveries I know that actually came from doing a massive simulation on modern computers, okay? And so this is what the dark matter actually looks like. And it turns out that all this dark stuff has a memory. Basically, stuff is coming in. Imagine all this is just pure dark matter and forming the central galaxy, a continent in the center, but leaving all these blobs behind because things just do not mix up that completely. So the new side, the realization now is our so-called dark halo should really be full of lots and lots of dark galaxies, and the race is on now to try to figure out ways to prove this, to see them, okay? And, the more massive of them may get some light in and turn out to be things like the Magellanic Clouds. We measure lots of faint dwarfs. Okay, but there we are. Okay. So let me end with showing you some interesting views of how structure forms as seen on the computer. So first of all, we begin with some very large region that's millions of, in fact, billions of light years across. That's 3 billion light years. And we're looking at structure develop in the dark matter. This is pure dark matter. And so you're seeing concentration of things emerging together. And what we're going to see forming in a moment is just a cluster of galaxies in the central region. Okay? So all of these node points are potential galaxies where the dark matter is streaming together. Okay, and so if I were to take the computer, this would be its prediction of a galaxy, and this is what we see. So clearly, there's an immense difference between what we see and what we predict. And the reason is that many of these dark clouds, contain gas, and the gas mixes up. Eventually it makes stars, in some region that's around here and spinning and so forth. But all of this dark stuff is out here somewhere and is a prediction of our theory. And so, but what I'm not going to do in this lecture is talk about that, but I just want to focus on what we can see, okay? Okay, so let me begin with one or two new simulations of how, when you put in the material that we can see, what things look like. Okay, so here you can see structure developing in this large box of the universe, again, millions of light years across. And now this is the stuff that we can see, not the dark matter. So the stuff that we can see is highlighted in these different colors. Okay, and so that's one simulation from the group at Oxford. Let's look at another one. I want to zero in a little bit. Okay, so there are several groups around the world. That was a UK version. This is the Dutch version of similar structure developing in the universe. So one does beautiful things with these simulations now. It's just, I find it stunning to look at these things. It's not to say this is reality. This is a model. You have to remember that. But it's our understanding of how all these ingredients fit together and how we're going to zoom in and eventually things merge together, and eventually the stuff we can see, the clouds merge together, and eventually we'll make galaxies, not just one galaxy, one big one in the middle, but many smaller ones around. So here you see the merging process of things coming together. And the baryons are sticky clouds. They merge together. The dark matter, a lot of it gets left behind. Okay? And then my final simulation, I want to show you how let's look at the Milky Way. And this is another view from the UK, from the group at University College London. So this is a beautiful simulation. If we can get it to play. So now we're just focusing in on the Milky Way, and I want you to see how that might have formed. So it's a thin disk, and here you see the spheroidal part forming. And again, this is our best reproduction of how our galaxy might have formed over, a long time, hundreds of millions of years. So this is, so one can do pretty incredible things. Okay, so let's see. Let me, I think I'm going to have to race ahead a little bit here. Okay, so just to finish, this is the reconstruction of how the luminous bits of the Milky Way might have formed. This is supposed to be the Milky Way, stars in orbits. And some of these satellites were shredded on their way in and leave these amazing streams behind. And the incredible thing is that when we look at the data, you see some very, very faint things, which are shredded galaxies from the past, and you see evidence for these streams, and maybe this is the best way to look at a nearby galaxy. And when you this was taken with an amateur's telescope, actually. It's a very, very deep observation, with a large field of view. This is the galaxy, and you see these streams around it, which are the relics, the luminous relics of the clouds of ordinary matter that eventually mostly merged into that galaxy. And our numerical simulations are able to so this is on the computer, what you predict. You can see that, when you see pictures like this and you can make models like this, you think you may not have the unique explanation, but you have more confidence in your ideas about dark matter. And some of these galaxies are so completely. Let me just end with this. This is one of these newly discovered galaxies, just shreds of nothing out there in the distant parts of the Milky Way. I mean, you wouldn't even know it was a galaxy, except that you can count stars. It doesn't look like your normal diffuse galaxy, right? But here it is. It presumably was once more compact, forming many stars, but the gravitational violence of its surroundings as it passed through the Milky Way ripped it apart. But this is testimony to these things really do. It's not just fantasy that we look at. Okay, so these are just cartoons. Let me just, I'm going to leave out black holes. Let me end with, this was finally how Hubble arranged the galaxy sequence when he tried to classify things together, the galaxies I've talked about. And our Milky Way is just one part in here somewhere, this type. And these are the galaxies with big spheroids. And completely spheroid. One sees all these weird things. Okay, to conclude, I would say that we really are nothing special. You know, the Milky Way is just one galaxy of many, and this is one of my favorite quotes. Our galaxy is only one of millions of billions in this amazing and expanding universe. So, thank you.